Slide 1. Welcome to Networking and Health Information Exchange Basic Health Data Standards. This is Lecture C. This component, Networking and Health Information Exchange, addresses what is required to accomplish networking across and among disparate organizations who have heterogeneous systems. As one might imagine, this topic covers a lot of territory fraught with new topics and a lot of acronyms. My apologies, but that is what it is. I suggest you keep your glossary beside you as you study this material. Unit 4 covers Basic Health Data Standards and consists of 6 lectures. Over these 6 lectures, we will identify the set of standards necessary to establish semantic interoperability. In Lecture C, we continue to introduce common, controlled vocabularies. The fact that it takes 2 lectures to cover just the top few controlled terminology sets gives an indication of how complex and confusing the issue of what terminology to use is. It is important to remember that much of what we hope to accomplish in terms of using HIT to enable a network of seamless care depends on resolving these issues. No one set is enough. Mapping between sets results in a loss of information. Slide 2. The objectives for this unit, Basic Health Data Standards, are to understand why it is necessary to use a common set of data elements with common names to be able to exchange and understand data from other places. Understand what is meant by semantic interoperability. Understand many of the sets of controlled vocabularies in use today, how they are used, and who requires their use. Slide 3. Additional objectives for this unit, Basic Health Data Standards, are to understand the use, purpose, and interrelation among sets of controlled vocabularies in use today. Identify the more common controlled vocabularies in use today: ICD, CPT, DRG, NDC, RX norm, and LOINC. Identify the more common controlled vocabularies in use today: SNOMED, medicine, MEDRA, nursing terminologies, MESH, and UMLS. Understand data elements, attributes of data elements. Slide 4. Additional objectives for this unit, Basic Health Data Standards, are to understand contribution of master metadictionary of data elements to semantic interoperability. Explain how data structures can be built from basic data components. Explain how templates and archetypes facilitate networking and information interchange. And discuss clinical data architecture, CDA, continuity of care document, CCD, and continuity of care record, CCR standards. Slide 5. In Lecture C, we continue a discussion on the use, purpose, and interrelation among sets of controlled vocabularies in use today, and identify the more common controlled vocabularies in use today: SNOMED, medicine, MEDRA, nursing terminologies, MESH, and UMLS. Slide 6. The roots of SNOMED go back to 1928. It was started by the New York Academy of Medicine and called the Systematized Nomenclature of Diseases and Organisms, SNDO. It evolved into SNOP in 1965 under the efforts of the College of American Pathology, CAP. In 1979, the name was changed to the Systemized Nomenclature of Medicine, SNOMED. In 1999, with a new release of the terminology set, the words reference terminology were added to SNOMED, and it became SNOMED RT. In 2002, SNOMED, under CAP, merged with the Reed Clinical Classification System, a coding system used primarily in the United Kingdom, mostly by primary care physicians. The version became known as SNOMED CT, clinical terms. In 2007, the International Healthcare Terminology SDO was formed. HTSDO acquires, owns, and administers the rights to SNOMED CT and other health terminologies and related standards. SNOMED-CT is the current version and is a semantic network with definitions. SNOMED-CT continues to evolve and is growing in use around the world. Slide 7. As noted, SNOMED-CT was created by the merger, expansion, and restructuring of SNOMED-RT and READ codes. SNOMED-CT includes 344,000 concepts, 450,000 medical descriptions, 700,000 concept interrelations, and that number is increasing. It has been cross-mapped to ICD-9 CM, ICD-10, and LOINC. SNOMED-CT is considered to be possibly the most comprehensive multilingual clinical healthcare terminology in the world. HITC has issued affiliate licenses to 5,000 individuals and organizations in the world. It is the closest to a universal language there is, yet it still falls short of adequate clinical representation. The U.S. originally paid $37.5 million to HITC for SNOMED licenses. Today, SNOMED-CT is available without charge to any person or group in the U.S. Current dues for the U.S. are still in the millions of dollars. Slide 8. SNOMED-CT components include concepts, basic units of meaning designated by unique code, unique name, and description, including preferred term and synonyms. Descriptions, terms or names, synonyms assigned to a concept. Hierarchies. There are 19 higher-level hierarchies, each has sub-hierarchies. And relationships. Link concepts either within a hierarchy or across hierarchies. Slide 9. This example illustrates the hierarchical relationships of SNOMED-CT. The example shows a code for burn of skin that is modified by subcodes for severity, severe. A finding site, structure of skin between the 4th and 5th toes. In this example, the SNOMED-CT code represents the coding of a severe burn between the 4th and 5th toes and a laterality of the left foot. This SNOMED-CT code is generated from the data by combining terms from the different SNOMED-CT axes. A pre-coordinated term is one that exists as part of the coded set, that is, defined in advance. A post-coordinated term is composed just in time. SNOMED-CT can be very powerful. However, one of the problems with SNOMED-CT is that a data element can be coded multiple ways, making queries a challenge. Slide 10. SNOMED-CT is a semantic network. This figure illustrates semantic relationships possible with SNOMED. Semantic relationships are indicated by the is-a link. Other properties are represented by definitive links. This slide shows semantic representation for the term pulmonary tularemia. It is a tularemia and it is a bacterial pneumonia. Pulmonary tularemia has finding site of lung structure, has an associated morphology of inflammation, and has causative agent of Francisella tularensis. Knowledge can be embedded in SNOMED through these links. This representation provides significant power for queries by any of these relationships. In this example, pulmonary tularemia has finding site of lung structure, has associated morphology of inflammation, and has causative agent of Francisella tularensis. Slide 11. These are the SNOMED axes. Findings represented by F. Procedures represented by P. Body structures represented by anatomy, T. Morphology represented by M. Organisms represented by L. Substances represented by C. Physical agents represented by A. Occupations, social context, general, and other. These axes provide the vectors for the semantic network, so a composite code can be represented by 0 or multiple codes across all of these axes. SNOMED can be very specific and detailed. Again, queries may be a problem with this structure. Slide 12. Here is an example showing the semantic relationship coding of SNOMED using some of the axes. The highest level code is structured across the multiple axes of SNOMED. In this example, ruptured ovarian cyst SNOMED code D7-75111 is a disease SNOMED code D7-00000 and has morphology rupture SNOMED code M-14400 and has morphology cyst SNOMED code M-33400 and has topography ovary SNOMED code T-87000. Slide 13. Medicine is a system of standardized medical terminology developed by Medicomp Systems. It includes over 250,000 clinical data elements encompassing symptoms, history, physical exam, tests, diagnoses, and therapy. Medicine is available at no cost. However, all of Medicine includes a knowledge base linkage for which there is a charge. Medicine is used by the Department of Defense. It is the most comprehensive vocabulary for signs and symptoms. Signs and symptoms, or history and physical findings, are usually the last data category to be structured and coded. Slide 14. International Classification for Primary Care, ICPC, is very popular for use in primary care settings throughout the world, except it has little use in the U.S., probably because ICD-9 coding system is required for reimbursement. It is based on ICD. ICPC is used by individual family practices and group practices and is used to record primary care patient encounter. The coding system includes reason for encounter, chief complaint, and focuses on patient perspective. ICPC includes fear of disease, request for preventive services, and request for treatment. ICPC has been translated into 19 languages. The terminology system is included in UMLS. One of the concerns with ICPC is that the code is based on the body system. The same disease would be coded differently depending on the body system involved. For example, an ICPC code related to the circulatory system would start with K. For the respiratory system, the code would start with R. The specific item being coded is numeric. For example, heart pain is coded as K21, respiratory pain is coded as R21, and chest pain is coded as A21, where A represents a general category. Slide 15. Medical Dictionary for Regulatory Activities, MEDRA, is an international medical terminology used by regulatory authorities and regulated biopharmaceutical industry. MEDRA supports terminology for coding all medical data obtained during all phases of development and marketing. The categories are symptoms, signs, disease, diagnoses, indications, investigations, procedures, and medical social history. MEDRA is developed by the International Conference on Harmonization of Technical Requirements for Registration of Pharmaceuticals for Human Use, ICH, and is owned by the International Federation of Pharmaceutical Manufacturers and Associations, IFPMA. It is free for regulators but costs for industry. MEDRA is one of the few coding systems used for adverse events, mostly medication errors. Unfortunately, it is not complete. It has been translated into 9 languages. Slide 16. MEDRA is a unique 8-digit number, starting with 100000001, with new terms being coded sequentially. Examples are gastric hemorrhage, LLT, equals 10017789. Gastric hemorrhage, LLT, equals 1001771188. Gastrointestinal disorders, SOC, equals 10017947. Note in the example the difference in spelling and the different code. While this accommodates the different spellings, the different codes create a challenge to queries. The LLT means lower-level term, and the HLT is a higher-level term. There is an implied hierarchy. Slide 17. One could truthfully say there are a lot of nursing terminologies. The popular nursing terminologies are North American Nursing Diagnosis Association, NANDA, taxonomy, clinical care classification, patient care dataset, PCDS, Omaha system, AORN perioperative dataset, nursing interventions classification, NIC, nursing outcomes classification, NOC, and International Classification of Nursing Practice, ICNP. The terminologies are all slightly different, but as shown in a later slide, the overlap is large. Many of these codes are proprietary and charge a license fee. Slide 18. Nursing codes are used to define nursing care and are broken into 4 categories. There is a nurse terminology that has as its primary use each of the categories. The categories are diagnoses and judgments, NANDA, interventions, Omaha, outcomes, NOC, and goals, PCDS. Slide 19. This table shows the overlaps across the various concepts among the different nursing terminologies. The International Classification of Nursing Practice covers all of the categories. You might ask, why don't these terminology sets merge into a single system? The answer is the same for most terminologies, political and financial. NANDA, diagnoses, NIC, interventions, NOC, outcomes, CCC, diagnoses, interventions, and outcomes, PCDS, diagnoses, interventions, and goals, Omaha, diagnoses, interventions, and outcomes, AORN, diagnoses, interventions, and outcomes, ICNP, diagnoses, interventions, outcomes, and goals. Slide 20. Medical subject headings, MESH, is used by the NLM to index the medical literature. MESH terms are used to tag medical abstracts with concept-based information. If you write an article that will be indexed by the NLM, the authors are asked to include the appropriate MESH term. It was created to improve information retrieval. The 2009 MESH contains over 25,000 descriptors and over 160,000 entry terms, words that map to specific MESH descriptors. The MESH thesaurus has been used to map over 5,200 biomedical journals worldwide. MESH is free. MESH makes retrieving the medical literature much easier. Since the terms are selected by the authors, they reflect best the content of the articles. Slide 21. This slide shows an example of MESH terms. The MESH terms are arranged in a hierarchical structure to permit searching at various levels. This MESH example for pneumonia illustrates the hierarchical nature of MESH. For example, one level down from the base code of pneumonia is pneumonia bacterial. Next level down has 3 branches: Legionnaire's disease, pneumonia, pneumococcal, and pneumonia mycoplasma, and so forth. The complete structure is D011014, pneumonia, D018410, pneumonia bacterial, D007877, Legionnaire's disease, D011018, pneumonia pneumococcal, D011019, pneumonia mycoplasma, D009175, mycoplasma infections, D011002, pleuropneumonia contagious, D011022, pneumonia rickettsial, D011023, pneumonia staphylococcal, D001996, bronchopneumonia, D009956, ornithosis, D011001, pleuropneumonia. D011015, pneumonia aspiration. D011017, pneumonia lipid. D011020, pneumonia pneumocystis carinii. D011024, pneumonia viral. Slide 22. Unified Medical Language System is a compendium of many controlled vocabularies in biomedicine and health. It is designed and maintained by the NLM. Anyone can sign up for UMLS and have access to any and all of the contents. UMLS contains many tables supporting various linkages among its contents. Dr. Donald A.B. Lindbergh, director of the NLM, clearly defined the purpose of the UMLS in 1993. The purpose of the Unified Medical Language System is to improve the ability of computer programs to understand the biomedical meaning in user inquiries and to use this understanding to retrieve and integrate relevant machine-readable information for users. Slide 23. The UMLS has three knowledge sources. Metathesaurus, a multi-purpose, multilingual vocabulary database that contains information about health-related concepts, including names, codes, and relationships. It is a dictionary of concepts in which different strings are linked to concepts. Two strings pointing to same concepts are synonyms. Strings come from the source vocabularies. Semantic network, a set of semantic types that provides a consistent categorization of concepts represented in the metathesaurus and a useful set of meaningful relationships. Major groupings include anatomic structures, biologic function, chemicals, events, organisms, physical objects, and other. The specialist lexicon, a general English lexicon that includes both commonly occurring words as well as biomedical terms. The purpose of the specialist lexicon is to support natural language processing. The specialist lexicon contains over 20,000 entries. Slide 24. In summary, this table shows the main controlled vocabulary sets used for the different categories of data. The number of pluses indicates significant use in the U.S. ICD and CPT have a cost associated with them. The table shows what terminologies are used for what purposes. ICD, diagnostic tests, diagnoses, medications, and costs. CPT, labs, diagnostic tests, diagnoses, medications, and costs. DRG, diagnoses, reimbursement. NDC, medications. RX norm, medications. LOINC, labs, diagnostic tests. Nursing, medications. SNOMED, history of present illness, past medical history, physical exam, labs, diagnostic tests, diagnoses, medications, treatments. MESH, history of present illness, past medical history, physical exam, labs, diagnostic tests, diagnoses, medications, treatments, and UMLS, history of present illness, past medical history, physical exam, labs, diagnostic tests, diagnoses, medications, and treatments. Slide 25. All of these terminologies are in use today. Most institutions will use a combination of these terminologies as well as local terminologies. The current status of terminologies, at least in the U.S. at the present time, includes SNOMED CT, which is gaining momentum as the terminology of choice, LOINC, which is used for laboratory test names, RX norm, which is likely to be drug code of choice, ICD-X, which is required for reimbursement, ICD-9 and moving into ICD-10, and MEDRA, which is used for adverse events. Today's world maps among these controlled terminologies. If mapping between two controlled terminologies is perfect, then why do we need both sets? If not, then mapping must be accompanied with information loss. In any case, these codes are a distance from real clinical usage. A common global master set of data elements does not exist. Until it does, true interoperability remains a goal. Slide 26. This concludes Lecture C of Basic Health Data Standards. The complex problems caused by use of local terminologies and too many controlled terminologies continues to be an obstacle to interoperability. Until this problem is solved, the sharing and aggregation of data among disparate sites will result in a loss of information and be prone to error. Slide 27. Additionally, in Lecture C, we discussed a set of controlled terminologies that are used in healthcare and healthcare processes and included characteristics and examples of each terminology set. Comparison among terminologies was also highlighted.